All right, testing, testing, testing. Audio looks good. Cool. Here we go. And let me find my pen. There we go. Welcome, welcome, welcome to our 2022 FRQ roundup, where we're going to do all 5 of these practice FRQs as completely as we can in a limited amount of time. So I am going to go over all 5 here, including ones that we may have gone over in class, because I want to make sure that anybody who wasn't in class, didn't quite get it in class, or just needs a little bit more time outside has their opportunity to get it. So let's start with our first FRQ here from 2021, last year's exam. We've got this cyclist coming down a ramp and leaping over 6 cars. And it wants us to figure out, well, how long is 6 cars? What is that distance x0 in terms of everything else? The first thing we always want to ask ourselves is what kind of question this is. This is a projectile motion question, kind of obviously. So it's a kinematics question at its heart, but it also has an energy component in here as well. So the first part is energy, because what we need in order to do our projectile motion is we need to know what is the initial velocity of the biker coming off the ramp. This part is conservation of energy. What we can do is we can say that we start with M0 G H0 worth of potential energy. Now, you would be forgiven for just writing MGH, but we do want to try to use the symbols they give us whenever possible. Well, we follow distance H0, all of that turns into potential energy in this case. So I don't have to worry, by the way, about the fact that we're not going all the way to the ground, because I don't actually know how far the ground is. Anyway, we're basically setting the 0 of our potential energy right here to make our lives easy. So I can do this solution. You could also, by the way, just jump straight to it. It does say derive, but I don't think they'd be too bothered if you found this initial velocity as root 2g h0 pretty quickly. So that's the first part we need here, is that initial velocity. Now, once we've got that initial velocity, we need to realize that 2 things are going on. We have an x velocity here, and we have a y velocity. And of course, in projectile motion, the really, really important things to remember are that our x motion, our x velocity is constant. That is, there's no acceleration in the x direction. And so that means that our second kinematics equation in the x direction, if we want to find this distance x0, which is ultimately what we want, it's just going to be our x velocity times time. That is, it's going to be v0 cosine theta times t. Now, in the end, I am going to do a bunch of substitutions, but I'm going to leave it this way for now. Our next challenge is, of course, then to find t. How long does it take to do this? There's a few different ways to do it. What I think is the most straightforward way is to focus on the apex of our trajectory here, and to remind ourselves that at the very, very top, our y velocity is 0. And if we look in the y direction, if we list everything we know in the y direction, we know that our initial y velocity is v0 sine theta. We know that our final y velocity is nothing. And we know that our acceleration in the y direction is negative g. And if we want to find a time, we can put all these together and look at our first kinematics equation, which of course relates to velocity and time. So if I'm looking, where did I put that thing? Where did I put that thing? There it is. So if I'm looking in my y direction, I can set up my second kinematics equation. My final velocity is 0. My initial velocity is v0 sine theta minus g times t. And I can get that my time is v0 sine theta divided by g. In this case, though, I want to make sure that we note that this is only the time up to the apex. So in fact, our total time, if we want our total time, it's going to be twice that, because we got to go up and come back down. And now we're finally ready to put it all together. We know what our x distance is. It's v0 cosine theta times our time. Our time is 2 v0 sine theta. These should be theta zeros divided by g. If I gather all that together, that's 2 v0 squared sine theta 0 cosine theta 0 all over g. Now, this is pretty good. It's not quite enough to get us there because they, in fact, want it not in terms of v. They only want h, theta, m, and physical constants. So I do, in fact, have to substitute in for v0 squared. Fortunately, I know what v0 squared is. It's going to be 2gh0. And so now I'm going to do a little bit of canceling and simplifying. Hey, look, my g goes away, so it actually doesn't matter what gravity is in this case. And I end up with my final answer here, that my distance x0, I'll write it over here, is 4 h0 sine theta 0 cosine theta 0. This is a lot of work. I'm not going to lie. It's 4 points. It's a decent amount of work for this question, but still, you could get quite far, do pretty well on the question without getting all of these points. The important thing, and I'm just going to highlight this once and then try not to repeat myself every single time, is to note, in the event you get to this question or a question like this and you're like, oh, I can't figure it out, do literally anything that gets you an answer that works, right? Even if that means making it up, even if you're like, this distance is going to be h0, right? Like, okay, make it reasonable. It's not reasonable to say x0 equals g because one of those is a distance and one of those is an acceleration. But like, make something up that seems plausible. If you're really, really stuck, get as far as you can. If you can find the initial velocity, go for that. Figure out some way to get a distance and then move on with your life. Don't spend 45 minutes beating your head against one part of one problem. This was a 4-pointer, or sorry, it's a 3-pointer. Not even half the points in the question. A point for using conservation of energy to find v. So if you got root 2gh0, that's a point right there. And again, every point is good. For using kinematics specifically in the y direction and attempting to find the time the bicycle is in the air. So again, just noting, you could totally fail to find the answer. You could find v0 and then struggle with your kinematics equations in the y direction, trying to figure out your time and still get the second point. It's important. And why is that? They want you to know that you use the y direction usually to find time. If you know that, it's worth a point. You're showing them something. The third point here is for doing all of the other messy stuff to get x0. Please note, you don't actually need to simplify it. If you stopped here, you'd be okay. It might make other parts of the question a little more complicated, but you'd be okay if you stopped there. So that's 3 points for that one. Then we get what I like to think of as these proportional thinking questions, which is, that is not asking you to actually do the calculation, but if I double this thing, what happens to this other thing? I cut this thing in half, what happens to this other thing? So it's asking us what happens if we double the launch height in this case? Well, if we look at our equation, sine theta 0, cosine theta 0, most of this stuff isn't changing. In fact, the only thing that's changing is x0. So there's a sense in which this is just x0 equals a bunch of stuff times h0. And if I double h0, right? If I double h0, well, it's not h0 squared. It's not h0 like the square root or anything. If I double my h0, well, I multiply one side of my equation by 2. I multiply the other side of my equation by 2. So in this case, if I double h, I end up with twice the distance. So it went from 6 cars to 12 cars in this case. This is a 2-pointer, 1 point for any justification that attempts to use what they call this the functional dependence. This is to say, to realize that x0 just kind of goes as h0. There's no squared. They're directly proportional in this case of the horizontal distance on the initial height. And then a second point with again, for an answer consistent with what you got in part A. So if you made up something in part A, even if part A was wrong, make sure your answer is consistent with that. You're always counting on using your equation. So if you said something funky, if you said in the first one that your x0 was root 2gh0, then your answer to this one is actually root 6 root 2. which is like 8.5 cars or whatever, that would be consistent. If you put this and then put 12 cars, actually they're both wrong because they want you to be consistent. They want you to analyze the work you did. So once you start solving something, just follow your gut. Don't second guess yourself, because if you second guess yourself, you can actually wind up in a little bit more trouble. Last but not least, we want to draw a graph. Well, we know that our biker starts off at some positive velocity. So it says on the axis below, sketch a graph of the vertical component, so just Vy. And I really would go through and read these and underline things and write little notes to yourself. Immediately after the cyclist leaves the ramp to immediately before the cyclist lands on the second ramp. On the vertical axis, so they want me to write something on the vertical axis. Clearly indicate the initial and final velocity components. Okay, we'll get there in a moment. So I know that we start off at some positive y velocity, but as we go up, we should slow down. And it's really important that this be linear. Why should it be linear? Well, this is a velocity versus time graph. And the slope on a velocity versus time graph tells me the acceleration. The acceleration in the y direction should be constant. It should just be negative g. So it should have a constant slope in this direction. It should also end at precisely the same velocity that it started at, although in the negative direction. And then we write in the y velocity, which is our initial velocity sine theta. In this case, 2g h0 sine theta, from the positive that to negative that. Do pay attention. There's a couple other sketches, and I'm sure they'll ask you to sketch something. Just be careful of what they're asking for. They ask for something a little different every time. So just read it carefully and really understand what they want on this. I know it's hard to read things carefully when you're going fast and you're feeling under pressure, but read the instructions carefully because they want to make sure you can do that. 2 points here, a linear graph with consistent negative slope. And for a graph that starts and ends at the same velocity, albeit you've got to only use the required variables. So that one is, again, I think part A is the hardest part, but you could make up part A totally and then do a pretty good job on B and C and still walk away with 3 or 4 points, which was well above average for this question in 2021. All right, we talked about this one in class today, but I'm still going to go over it. We've got 2 pulleys with different radii. So we've got object 2 connected to this inner pulley of radius r0, and object 1 connected to this outer pulley of radius 2r0. And the very first thing it asks is, it says at time t equals 0, the pulleys are released from rest. That's actually going to be important. They're released from rest. And the objects begin to accelerate. And it wants us to derive an expression for the magnitude of the net torque exerted on the object. So let's remind ourselves how to calculate torque. Torque is our lever arm times our force. And in this case, if we're looking at the system kind of holistically, if we're just looking at the whole system, the reason this thing is moving one way or the other is because of gravity ultimately. There are going to be some tension forces and things, but ultimately it's gravity that's doing the work here. So if I look at object 1, object 1 is going to be pulling down this way with a force m0g, and it's doing it at a radius of 2r0. Notice it's all nice and perpendicular. I don't have to mess with sines or cosines. So the torque from this one is just going to be m0g times its radius 2r0. This one's going to be applying a bigger downward force, actually. I should draw it bigger, of 1.5 m0g, but at a smaller radius. Notice that I'm subtracting them because one torque is counterclockwise, one torque is counterclockwise, one torque is clockwise. Well, in this case, if I add these up, here I've got 2 mgr0, here I've got 1.5 mgr0. So my result in the end is, that's a fun width. My result in the end here is just 0.5 or 1/2. I like writing it as 1/2. Fractions for life, m0g, r0 in this case. It then asks us in question 2, object 1 accelerates downward after the pulleys are released. Why? Well, we declared this direction to be the positive direction, negative. Our net torque is positive, right? You could also argue that the torque from object 1 is greater in magnitude than the torque from object 2, so the object's going to rotate in the counterclockwise direction as that. So let's see how we did on that first section. This is 4 points in total. So a point for the correct expressions for torque, m0g times 2r0, and 1.5 m0g r0 for object 2. A second point for indicating that the two torques are exerted in opposite directions. You don't have to state that. If you're just showing that they're subtracted, that is plenty. A third point here for the correct answer in that case. And then for the fourth point here, any indication that object 1 exerts more torque than object 2 gets you there. So that's 4 points, 4 out of 7, right off the bat for doing some subtraction and saying one number is bigger than another. We then do a funky thing where the system is moving to the right. And then we snip string 1. And when we snip string 1, the whole thing kind of changes. Now we basically have a system that looks like this, and it's going to start rotating in the other direction. But that doesn't happen right away. Imagine that you've got a really big heavy wheel that's spinning counterclockwise. Well, if you start pulling it clockwise, it's not going to reverse direction right away. It's going to slow down, stop, and then reverse direction. So at the moment you cut the string, the wheel, the pulley is still rotating in the counterclockwise direction, but now the net torque is in the clockwise direction. And remember, net torque equals I alpha. If our net torque is to the right, is in the clockwise direction, our acceleration's in the clockwise direction also. So here, the moment we cut the string, our wheel is still spinning counterclockwise, but it's now accelerating in the clockwise direction. So it's going to start slowing down. It's going to start slowing down. My explanation here, I think, is that it's got angular momentum. It continues to spin counterclockwise for at least a little bit before it turns back. Now we're asked to sketch a graph of the angular velocity. It is so important that it started 0 because our system started at rest. You always want to ask, hey, where does my graph start? So it starts at 0. And then it is going to speed up. That's pretty clear. And the question is, how does it speed up? We got to remember, just like our previous graph, if our torque is constant, then our angular acceleration is constant. And if our angular acceleration is constant, then the slope of our graph should be constant. Please note, you want to take this out to the time of cutting, TC, here. And then the moment we cut the string, our situation changes. Our velocity is still positive, but now our acceleration is negative, right? Here we had a positive angular velocity and a positive angular acceleration. All of a sudden, we still have a positive angular velocity, but our angular acceleration is negative. And so what happens is this happens. We start to go the other way. So our angular velocity slows down, stops. And then now our angular velocity is negative. Now we're spinning the other way, but it takes a moment. Please note, just again, the instructions, this is our second sketch, include the entire time interval shown, but it doesn't ask us to do anything with the vertical axis. So you don't have to do anything with the vertical axis. This one is, what's interesting is this should actually be steeper. The second negative slope should be steeper than the first slope, but there's no points associated with that. And that's because the torque is greater. Before, our net torque was 1/2 mgr. Now it's 3/2. Now it's 1.5. So we actually have 3 times as much torque going the other way. Let's go take a look. B, a point for opposite direction. Please note, you will only ever get points for a correct answer and a correct explanation. If you do just one, you don't quite get where you need to go. So always justify. For the graph, we get 2 points here. 1 point for the first linear chunk. It's got to have an initial velocity of 0 and non-zero slope. And then it should change in sign. So positive to negative, negative to positive. There's no point associated with it being steeper in that section. All right, that one was okay. That one was all right. This one is a little stranger, but I do like it. I do like it. Here we have a new kind of toy ball, as they say, that somebody claims bounces perfectly elastically. Let's just pause for a moment and remind ourselves what the heck it means to be elastic. In elastic collision, all collisions conserve momentum. Every single collision conserves momentum. Elastic collisions also conserve energy. They also conserve kinetic energy. So elastic collisions also conserve kinetic energy. So in this case, we want to actually, this is, even though collisions are usually momentum, this is actually an energy question. And so we want to be really cautious here, or not cautious. This is a really weird question. So we want to read it carefully and think carefully. The student suspects, however, that no collision can be perfectly elastic. The student hypothesizes that the collisions are very close to being perfectly elastic for low speed collisions, but deviate more and more from being elastic as the collision speed increases. All right, so this is a strange question, but they will probably ask you some kind of lab question like this on the test. And what I want you to think is, if I handed you this ball and told you it's perfectly elastic, it maintains every bit of energy in a collision, you'd probably do one of two things. Either you would drop it from some height and see how high it bounces. And if it's perfectly elastic, it'll get up to exactly the same height. Or you'd like drop it or chuck it at something, right? Maybe you would throw it at the ground and you say, well, if it's perfectly elastic, then the velocity it hits the ground with, it should be going in exactly the same velocity in the other direction when it bounces off. It should keep every little drop of energy that it has. So there's actually other ways to measure it. These are probably the two best ways, what I'm going to think of as the height method and the velocity method. So if you get one of these on the test, I would just stop and think about physically holding the object and what would you do to test the claim that's been made. So for an experiment, we want to know what we're going to measure. I want to be careful, be very specific about what you're measuring. So if you're doing the height model, don't just say height. Because you're not just measuring height, you're measuring two heights. You're measuring initial height and final height. In this case, you're measuring initial height and final height. You don't actually need a timer for number one. Technically, that's the only thing you need to measure. You just need to measure two heights. Similarly, if you're doing the velocity version of the lab, you got to be really careful. Do not say you're measuring velocity, because you're not measuring velocity usually unless you have a radar gun or something like that. How did we do this in every single other lab we did? Well, what we did is we took a meter stick and we used a video and we measured position and we measured time in order to calculate velocity. So be really specific. When they say measure, they literally mean measure. What is something where I can look at my data and write down a number, no calculations, no anything else. We're going to calculate the velocity, but we're not measuring it. For the equipment, well, if I'm doing height, I probably want a meter stick. I think you also want a video camera for the height version of the lab, because I think you can imagine eyeballing exactly how high the ball gets back up to is probably challenging. So having some kind of camera so you know exactly where it was released and exactly where it got up to is good. For the velocity version of the lab, we're also going to want a meter stick. We're also going to want a camera. And the big difference is if we're calculating velocity, we want a timer. Describing the procedure, I was looking on in people's papers today. They were doing a pretty good job. It doesn't have to be a paragraph, as we'll see in a moment. It can be pretty brief. The important things to hit here are you need to do multiple trials and you need to vary something. You need to change part of your experiment. So if I'm doing the height lab, I don't want to drop it from the same height 10 times. What I want to do is I want to drop it from 50 centimeters and 75 centimeters and 100 centimeters and 150 centimeters. I want to drop it from 5 or 6 different heights so that I can see how the relationship changes as I drop it from different heights. So it's really important you try different heights, or if you're the velocities, throw it at the ground at different speeds or drop it from different heights, right? You need to manufacture somehow different velocities or different heights. All right. This is a 12-point question. This is a big question. So A is worth 4 points. And we've got a point for an overall plan that works, that could be used to compare mechanical energy before and after a collision. The second point is for a conceptually plausible plan to measure the positions or speeds before and after the collision. So either height or speed. 2 points here for having lab equipment and measurement procedures well specified. And again, there's specifically a point, trials of different pre-collision speeds or different pre-collision heights. You've got to vary something. So this is actually a fine result. This is literally their example. I could measure the drop height of the ball and the bounce height. I could use a meter stick to measure the heights and a video camera to record the ball's motion. Place the meter stick upright against the wall, drop the ball from 10 different drop heights using the video camera. Done. Not a paragraph, that's 4 points. That's the whole thing. Like, write as much as you think you need to, but they're not looking for a book, right? They're looking for a clear description. Just to check, you can hear me okay, right? I hope so. Yeah, excellent. All right, if you're doing the velocity version of the lab, it looks about the same. They use a photo gate. I would stick with your comfort. We've been using timers and video cameras for velocity measurements. I would do the same thing for velocity calculations. How would you represent the data? Well, here, depending on what you're doing, if you're doing the height method, I would probably put one of my heights on one axis and the other height on the other axis. Similarly, if you're calculating your velocities, I would probably put one velocity on one axis and my final velocity on the other axis, noting maybe you want to do the absolute values or just the speeds, or recognize that if one of your velocities is positive, the other is going to be negative because it's bouncing. In both cases, if energy is perfectly conserved, you would expect that the two would be identical. And so you're going to want to maybe sketch the graph or explain. And what would you expect to see? Well, if the data are perfect, right? If the ball is perfectly elastic, it should stick on that line, right? My final height should be equal to my initial height. If the ball is not, in fact, perfectly elastic, as the student suspects, we would expect that this graph would curve this way, right? The student suspects that as I drop it higher and higher, or it's going faster and faster, it should deviate from being perfectly elastic. That is, the initial height should be less than, or sorry, the initial height should be, my initial height should be greater than my final height, right? It should start out high and maybe not bounce up quite as high, which is what we would expect. So you want to be able to explain yourself there. A sketch really does make a big difference, although you should provide some explanation as well. C is written really weirdly, so let's talk about this. A student tries it and something goes really wrong. They immediately conclude that they did something wrong because they got data that fundamentally doesn't make sense, that violates a basic physics principle. And they want you to give an example. Well, let's take an example. Let's take the height example. What could be something that would be really unexpected? Well, if I drop the ball from 1 meter and it bounces up to 1.5 meters, there's a problem here, right? It shouldn't bounce up higher than it started. So the graph that they might get would look something like this, right? Or similarly for velocity, you send it in at 1 meter per second and it bounces back at 2 meters per second. So either of these graphs in blue would be a big problem. And specifically, the physics principle that would be violated here would be conservation of energy. That if your ball bounces higher than it started, it somehow ends up with more energy than it started with. You have done something wrong in the experiment. Either maybe you were throwing the ball down, maybe you weren't quite dropping it. Maybe something's happening with the floor where it's rebounding and getting a little bit of extra energy, but like something's gone wrong with your experiment where you're ending up with more energy than you started with. Again, this is a 12-pointer, so A was worth 4 points. B, is really small. B, also worth 4 points. 4 points for describing how to plot or otherwise represent the data in a way that can be used to test the hypothesis. Making a graph is almost always the best thing to do. You could describe how to compare the post-collision to pre-collision energy. So an example, right, that they've got here is make a graph of the bounce height as a function of the drop height. If the data are consistent with the hypothesis, then the data will lie close to the line for low drop heights and lie below the line for high drop heights. They suggest making a graph of the change in velocity, the change in the square of the velocity as a function of v. And they're expecting, okay, this is their example. You don't have to do it that way. Delta v squared. They're saying basically that this should, for low speeds, be pretty darn close to 0. You lose almost no energy, and then you start to lose a bunch of energy as you go higher and higher. And then for part C, again, what they're asking is really just drawing a table or graph that shows a big problem. And specifically, there's it says there's a variety of different physical principles you could use, but conservation of energy is the whole problem is about conservation of energy. So conservation of energy is kind of the low-hanging one. This one's a little weird. There will probably be some kind of like design a lab question. And so again, the key points here are think physically about how you do it, right? If somebody hands you a ball and says this ball is incredibly bouncy, you're going to drop it and see how high it bounces. Think carefully about what you have to measure, what tools you're going to use, be very specific, and make sure you're doing multiple trials with something changing. All right, on to our Atwood machine one here, another Atwood machine. We've got here an Atwood machine. The mass of block 2 is greater than the mass of block 1. So I want to draw some free body diagrams. They are careful to say here, the relative lengths of vectors should be consistent. That is, if one vector is drawn bigger than another, it should be because the force is bigger. So I'm going to go ahead. I know block 2 is bigger than block 1. So I'm going to go ahead and draw M2G pretty big. I'm going to draw M1G pretty small. Well, that's not the only force. I also have tension, right? Tension being up. Now, here's the thing. If we think about this system, which way should M2 go? It should go to the right. It should go down. It should go to the right, right? So which force should be bigger, gravity or tension? Gravity, yeah, absolutely. So I drew 1, 2, 3 for gravity. I'm going to make tension smaller because, again, it wants us to draw them in some kind of relative proportion. If I drew tension as 2 units here, I need to draw tension exactly the same over here because tension should be the same on both ends of the string. Notice what that ends me up with is this one has a net force upwards. This one has a net force downwards. That's nice. That's awesome. Don't actually draw those extra vectors on there. Let's go ahead and just take a look how we did on the free body diagram. This is 2 points, 2 out of 7. Not bad. 2 points for drawing 2 vectors starting on the dot that point upward, have the same length and are labeled as the tension force. You can label it T, you can label it FT, you can label it tension. You could say, this is the tension force vector. That's fine. You got 2 of them. They have to have the same length though, in order for you to get that point. You need 2 gravitational forces, where the vector for block 1 is smaller than the vector block 2. And then there's opportunities to actually lose points, which is interesting. If you draw any extra vectors, you draw friction, you draw a normal force, you lose a point. Also, there's a point that you can lose if your vector lengths don't allow the system to accelerate in the proper direction. So let's imagine what that means. Let's say I draw M2G bigger than M1G, right? And I draw my tensions the same length, right? Well, I'm actually going to earn 2 points at first, because if I do this, I'm going to get the point for the 2 gravities being downward and being different lengths. I'm going to earn a point for the 2 tensions being upwards and being the same length. The problem is that this free body diagram I've drawn has this one accelerating upwards. That's fine. This free body diagram also has mass 2 accelerating upwards. So the free body diagram I've drawn has both masses going upwards. So if I drew this, I would actually get 2 points and then I would lose a point for that. So be a little cautious on that. It then wants us to derive the magnitude of the acceleration of block 2, recognizing that both blocks actually will have the same acceleration. There's a longer way to do this and a quicker way to do this. The longer way to do this is to set up the Newton's second law for each block, m2g minus t equals m2a. And for the other one, it's t minus m1g equals m1a. So you do F equals ma for each block individually. And then what I can do is I can take these two equations and I can add them up. And if I add them up, notice I have a minus t and then a plus t. Those are going to cancel out. And I end up with m2g minus m1g equals, okay, well, this is m2a plus m1a, but it's the same acceleration. So I can just kind of add the masses up. You know, if this is 3a and 2a, I'm going to end up with 5a on the side. In which case, I can now divide to solve for the acceleration. So the acceleration of the system is, I could leave it here as m2g minus m1g all over m2 plus m1. I can also factor out the g, and what I get is m2 minus m1 all over m2 plus m1 times g. There is a second way to do this, which is to say, hey, what's the external force that's acting on my system? Because I've got tension and whatever, but really, what's the force from outside that's making this whole thing move? It's gravity, right? I've got m2g here, and I've got m1g here. So if I think about my whole system and try to do F equals ma for my whole system, the net force for my whole system, I could write as m2g minus m1g. And that seems a little weird because the two forces are both down. The reason I'm subtracting them is m2g is trying to pull the system one way, m1g is trying to pull the system the other way. So they're actually going to fight each other. But those forces together have to move my entire system, right? So my total force on the system moves my total mass on the system. And you'll notice we end up in the same place we did before, and we can solve it there. You don't have to do this in order to get a good number of points on the question. If you draw your free body diagram correctly, that's 2 points. B here is 3 points. A couple different ways to do it. Again, a point for writing Newton's second law for block 1 and for block 2. So frankly, even if you didn't solve it, if you wrote Newton's second law for both blocks, that's 2 out of 3 points right there. And this is why I say don't give up. If you might not know how to solve it, you might forget to add them or how to solve the system of equations, but don't let that stop you. You've drawn a free body diagram. If you write Newton's second law for each of the blocks, you'll get 2 out of 3 points because that's 2/3 of the process. So don't shortchange yourself. Don't be like, oh, I don't know how to do it. I'm gonna have to write it. Last but not least, we now insert a third block into the system. And we ask what happens to the acceleration of block 2? Well, we haven't actually added more force, right? We haven't added any more force. That is, it's still just gravity on 1 and 2 that's moving the system. However, what have we done to the total mass of the system? We've increased it. So there's no extra force, but we've increased the mass. Well, in my book, if the force stays the same and the mass goes up, that means the acceleration is going to go down. So we've increased the mass of the system while not actually affecting anything. If you ran the actual numbers, what you'd find is the acceleration of the system is now m2 minus m1 times g all over m1 plus m2 plus m3, right? The total mass is just on the bottom. So our acceleration goes down in this case. This is a 2-point question. So again, you could totally skip B. You could do A and C and get 4 out of 7 points, which is not bad. So, focus on your areas of strength sometimes. You could not solve B. You could do A, write down Newton's second law, and then be like, nope, and then do part C and get 6 out of 7 for the question without ever actually solving the system's equation. So, you don't have to do everything to completion to get max points. Here, 2 points for noting that the acceleration of the new system is smaller because the mass of the system is bigger. That is plenty. All right. Moving on to the very, very last FRQ. This is actually one from AP Physics C. It's ever so slightly more complicated, but I do think it's a good example of the kinds of things you can still do. So it asks us to draw a free body diagram here, noting that the friction is not negligible. So here we're going to have some kind of pulling force or tension force from the string. We're going to have mg down, of course. We'll have some normal force up. And we will have friction pulling back, because they, of course, tell us that friction is not negligible in this case. So for drawing this free body diagram, you'd get 3 points. It's worth noting for Physics C, the FRQs are worth more points. And so 3 points is a lot, but maybe less by the standards of AP Physics C. A point for force to tension, a point for force to friction, and a point for both forces in the vertical direction in this case. They're not worried about the relative magnitudes of the vectors, so you're good in that case. And then they give you a bunch of data, and they ask you to make a graph, which I didn't actually put the data in here, did I? That's fun. I didn't actually put the data in here. So let me go grab the data real fast. Stand by as I get the data. Really? Okay, there it is. Apologies for the delay. I didn't actually put the data table on my slide. Come on. There's the data table. All right. Nice. All right, so here is our data table, and they want, see, I thought I put it on there. Here's our data table, and they want us to make a graph. So here, this is something they do less of in Physics 1, but it's still a thing that they could conceivably ask. We got to set up our graph here. So if I'm looking at my acceleration goes up to about 0.7. I'm going to choose here to go 0.2, 0.4, 0.6, 0.81. There are other options you could do, certainly, in that case. For our force sensor reading, I'm going to go 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7. And then I just got to go make my graph, which I'm going to sort of eyeball here, 0.32 point. So you got to look at these things. 1, 2, 3, 4, 5. So these are 0.02, 1, 2, 3, 4, and these are like 0.04 in this direction. So I come up 3. So I got a point there. I got a point here. I got a point here. I got a point here, and I got a point here. And then they ask you to draw a best fit line. This is where you're going to want to take the ruler that you will have. Don't play connect to the dots. Just draw the best line you can that seems to fit the data as best you can. If they ask you to do this, there's going to be some wiggle room. So don't worry about getting it precisely right. It then asks you to use the straight line from the graph to calculate the mass of the part. Well, I want to note, don't use data points. If they say to use the line, use the line. So if I'm looking at the line, in fact, if they ever ask you to do this, to draw a free body, to draw a line of best fit, you should basically ignore the data points from then on and only use the line. Because the data points are subject to experimental error. Here we're looking at our line. So this is acceleration and force. This is not, the relationship between force and acceleration, we know, is net force equals ma. The thing is, this is not our net force that's shown. What we've actually got is our tension. This is our tension force. minus friction equals ma. So what we're actually looking at is our acceleration on the y-axis. So our actual acceleration sort of looks like this. Notice, here's our y data. Here's our x data, right? Kinetic friction is a constant. So this looks like y equals x over m minus some kind of constant. This is the equation of a line. And in this case, specifically, if we look for the slope of our line, the slope of our line is going to turn out to be 1 over the mass of our object. Why is it 1 over the mass? Well, we're used to y equals mx. And it's unfortunate here that m is both slope and mass. What is multiplied here by my x? Well, it is 1 over m is my slope here. I'm not going to go through the whole details. If you draw this line, draw it the best way you can, and then really count those boxes carefully. I ended up with a slope of about 2-ish, which gave me a mass of 1 over 2 of about 0.5 kilograms. You do need to find the slope here. The official answer is like 0.47, but really anything in the 0.5-ish range is pretty good. What about the magnitude of the force of friction on the cart? Well, look at one thing about this line is it has an intercept, right? And think about what this intercept means. It means in this case that if I'm pulling with a force of this, my acceleration is nothing, right? Well, if I'm pulling and I'm getting no acceleration, that means my forces are balanced. So this point is where my pulling force equals my force of kinetic friction. That's where my forces are all balanced. And if I go look at this, this looks like it's just shy of 0.3, 0.28 newtons or something, it looks like for there. So being able to interpret different features of your graph is important. Like I said, this is a physics C question. I really liked it, but it is probably a little bit more challenging than we would get on the actual exam. It's potentially fair game for that. So let's see how we would have done. Again, physics C, the point scale is a little different. 3 points for our graph, a correct scale that uses more than half the grid, correctly plotting the given data, and drawing a straight line consistent with the given data there. And then we get a point for correctly calculating the slope, and a second point for finding the mass of the cart, or for looking at the intercept to find the force of friction. All right, and that wraps up our 5 practice FRQs. There were a bunch of different ones. There's almost the lab design question, graphing, writing free body diagrams, and should be hopefully a fairly good idea of the kinds of questions that you're going to see, though obviously I don't know exactly what you're going to look at on Thursday. All right, thank you very much, and take care of yourself. All right.